Hello everyone. I'm Woosuk. This is Zhuohan. Today, we are more than happy to present our paper, Efficient Memory Management for Large Language Model Serving with PagedAttention. This project is joint work with our colleagues at UC Berkeley, Stanford, and UCSD. Let's get started. Arguably, we are in the era of LLMs. LLMs have shown remarkable capabilities in a variety of tasks from chatting to content creation to programming. Some of these applications, such as ChatGPT and GitHub Copilot, are already changing our lives. And not surprisingly, a key part of this application is systems that serve the LLMs using GPUs. However, we've noticed that serving LLMs is surprisingly slow and expensive. For example, a single GPU managed to serve less than 1 request per second for moderate-sized models and inputs. This means you will need a ton of GPUs if you actually build production-scale services using LLMs. Indeed, the high cost of serving LLMs has been a major challenge for many in the field. Even hyperscalers like Microsoft struggle for securing enough GPUs for their LLM-powered services. To understand the problem, let's look into the inference process of LLMs. First, the user provides a prompt consisting of multiple tokens or multiple words. The prompt goes through the model, and then we get the next token to the prompt. The next step, we feed this new token back to the model and get a second output. This process is repeated until the sequence either reaches its maximum length or generates certain tokens for stopping. So why is this process slow and inefficient? Intuitively, it's because the sequential dependency between the output tokens, which is inherent to the model design, makes it difficult to fully utilize the parallelism in GPUs. And a good solution to this is to batch multiple requests together. Through batching, we can feed the model with a larger amount of work at every step, and thus better utilize the parallel hardware. But does that solve our problem entirely? Unfortunately, no. The challenge is, to achieve high GPU utilization, we have to batch sufficiently many requests together. However, we observe a constraint. The batch size is often limited by the inefficient memory management for KV cache. What is KV cache? KV cache is a unique component in the inference process of LLMs. When processing an input token, the model computes intermediate vector representations of the token, specifically the vectors called attention keys and values. In addition to that, the model uses the vector representation of all the previous tokens in the sequence to predict the next token. So these states of the previous token should be kept in memory until the sequence finishes. And they are called KV cache in the ML literature. KV cache dynamically grows as the model generates new tokens. It also shrinks as the states are deleted once the sequence finishes. And importantly, KV cache is huge. The state for each token takes up to 1 megabyte in space, which means the state for a single request can take up to several gigabytes of memory. So how do previous systems manage the memory for KV cache? Given a prompt, they pre-allocate contiguous space of memory to the request maximal length. This is useful convention in traditional deep learning workloads where the shapes are static. However, this turns out to be highly inefficient for LLM inference, where the sequence lengths are highly dynamic. Specifically, this leads to internal fragmentation due to the unknown output lengths, and also external fragmentation due to the non-uniform maximum lengths across different requests. According to our profiling results, the memory waste was significant. Only 20 to 40% of the KV cache space was actually utilized to store the token states. The rest was merely wasted by fragmentation. So how do we solve this? Our solution is PagedAttention, which is application-level memory paging and virtualization for KV cache. As we all know, OS uses paging to reduce fragmentation, and it uses virtual memory for efficient and elegant space multiplexing between processes. And what PagedAttention does are basically the same. Let's dive into it. To begin with, we partition the KV cache space into an array of KV blocks, just like paging. A KV block is a fixed size chunk of memory that can store token states from left to right. In this particular example, the block size is 4, which means we can store 4 token states in a block. Then we virtualize the KV cache into logical and physical KV blocks. In the logical view, the tokens are stored in a natural fashion. They are stored in consecutive blocks where the order is preserved. In the physical view, on the other hand, the tokens may not be stored in adjacent blocks. And the mapping between the two is stored in a new data structure called block table. For the attention operation, we implement its GPU kernel to utilize the virtualized KV cache. That is, the kernel patches the blocks using the block table while computing attention mechanism on the fly. Please note that the memory indirection here introduces 10 to 15% slowdown for this particular operation. However, this trade-off will lead to higher memory efficiency and overall throughput at the end of the day. PagedAttention also comes with simple memory management. We just append new tokens to the last block of the sequence and allocate a new block on demand when the last block is full. Let's quickly analyze the memory efficiency of PagedAttention. First, it has minimal internal fragmentation. This is because the internal fragmentation only happens at the last block of a sequence, which means the number of the wasted tokens per sequence is bounded by the block size. In practice, the block size is orders of magnitude smaller than a typical sequence length. Therefore, internal fragmentation is very small. Second, PagedAttention does not have external fragmentation since every block is uniform in size. Putting these all together, we utilize over 96% of the KV cache space on average, which is 2.5 to 5 times improvement over the previous systems. Just a quick note on how to configure the block size. Intuitively, we want to find a sweet spot between spatial locality and internal fragmentation. To determine the optimal size, we conducted benchmarks on different data sets and found that block size 16 works generally well in practice. Now I will pass it on to Zhuohan.
Hi everyone, this is Zhuohan. So just now, Woosuk talked about how the PagedAttention reduces memory fragmentation and improves the serving throughput. And another big advantage of PagedAttention is about memory sharing. For example, it's common to sample multiple candidate outputs with the same prompt from an LLM. In such a case, the computation and also the KV cache memory for the prompt can be shared between the parallel output samples. PagedAttention can naturally support the sharing in this decoding scenario. On the slide, we show an example of generating 2 parallel samples. For the prompt part, PagedAttention will only compute once and store only 1 copy of the KV cache in the physical blocks. Since both samples share the prompt, we map their logical blocks to the same set of physical blocks. As the next step, the 2 samples get different output tokens. Here, we use the copy-on-write technique from OS virtual memory to make sure there will be no write conflicts. Specifically, in this case, we copy the last prompt block to let the 2 samples write to different KV blocks. And after that, the 2 samples can continue generation independently. Note that all the prompt blocks, except the very last block, can be shared between the parallel samples. When the prompt is long, the sharing can greatly reduce both the compute and the memory usage. A more complex sharing example is the beam search decoding algorithm. Different beam search candidates not only share the prompt, but also share the many intermediate output tokens and their KV caches. The sharing pattern can also dynamically change as the beam search progresses. We can see that the sharing pattern here is very similar to the fork tree when you call nested fork in OS processes. This pattern can be effectively supported by our paged KV cache memory. In our experiments, we show that via sharing, we can save 30% of memory for parallel sampling and more than 60% for beam search. In summary, PagedAttention can support efficient sharing to further reduce memory usage, hence increase the serving throughput. Although PagedAttention can help save a lot of memory, because the output lengths of LLMs are unpredictable, we will still potentially run out of all physical blocks and cannot allocate space for new tokens. Like in this example, we have no space to save the KV cache for the new tokens of request B. In this case, we need to free the KV cache of some requests to let others run first. Here, we have two options to preempt a request. The first option is the classical idea in virtual memory. We can swap the GPU KV blocks to the larger and cheaper CPU RAM. And the second option is recomputation. Since we can fully reproduce the KV cache with the tokens of a request, we can just delete the KV cache and recompute it during recovery. For our scheduling, preemption, and recovery policy, we would like to highlight the following points. First, we always swap or recompute the whole request, since all previous tokens are required to generate a new token. In this case, keeping partial KV cache does not help on generating new tokens. And second, for swapping, smaller KV block sizes will have higher overhead, since many small data transfers are launched in this case. And third, recomputation is actually surprisingly fast, since we can parallelize the computation of all tokens on GPU without the need to sequentially generate the tokens one by one. And we compare the speed of swapping and recomputation. And we find that when block size is small, recomputation can be faster than swapping. Overall, for simplicity, we use recomputation whenever possible and use first-come, first-served policy to choose which request to preempt. In summary, comparing with virtual memory and paging in the operating system, our techniques share many analogies, but also have some key differences. First, both OS pages and KV blocks use paging to reduce memory fragmentation. Second, sharing pages across processes and sharing KV blocks across samples both help reduce memory waste via sharing. And for differences, we would like to highlight that first, our block table is tiny compared to the actual data. So we use a simple single-level block table as opposed to the multi-level table in the OS. And second, because we are working on LLM serving application, we can perform request-level preemption and recomputation-based recovery. We implement PagedAttention in VLLM, an end-to-end LLM serving system that supports distributed model parallel execution for large models. VLLM has a centralized engine that manages the block table, and at each step, the centralized engine sends the memory commands to the GPU workers. The cache engine in the GPU workers will actually allocate the physical blocks according to the memory commands, and then the worker will execute the model distributedly with model parallelism. And more specifically, we implemented VLLM based on PyTorch and Hugging Face transformers and used Ray and Megatron LLM for distributed execution. For the evaluation, we measure the serving throughput of VLLM and other baselines. We use two real-world LLM datasets for the input and output distribution: the Alpaca instruction following dataset and the shared GPT dataset for conversation data. We have two sets of baselines, the NVIDIA faster transformer baseline and the previous state-of-the-art Orca. For Orca, since its memory usage depends on the prior knowledge of the output length, we further set 3 sub-baselines, which assume they either know the exact output length, or over-reserve the space for 2x, or over-reserve to the maximum possible output length. Due to time limit, we will share part of the results here, and you can find more in the paper. For decoding one output with 13 billion parameter model and the shared GPT trace, we can outperform all baselines. And specifically, compared with Orca power of 2, we can achieve 2.4x higher throughput. And if we look at the average number of batch requests at each step, we can see that indeed VLM and PagedAttention can batch many more requests compared to previous works. When evaluating the same model with beam search on the alpaca trace, we can see that with a larger beam width, PagedAttention can exploit more memory sharing opportunities and can further increase the speed up from 1.8x to 3.5x. We open sourced VLM in June and released the system as a Python package. And since then, we have been widely adopted across many open source projects and across the industry. We have also received many open source contributions. In conclusion, PagedAttention improves the memory efficiency of LLM serving by 2.5 to 5x by minimizing memory fragmentation and enabling sharing. This brings up to 4x higher serving throughput compared to state-of-the-art. VLM with PagedAttention has become a vibrant open source project that gets widely adopted. You can learn more about VLM and PagedAttention with the link on the slides. Again, happy to be here and happy to answer any questions.
Hi, at first, thanks for your impressive talk. And I actually have a question about opening your VLM SOS as an open source. Because as far as I know, I guess the company named Friendly AI has a patent for selective batching technique, which is one of your comparison baseline. And I'm curious that is it okay to share the code which is protected by the patent? Yeah.
Okay, so I think, yeah, this is a research paper, and the Orca baseline in our paper is like we fully reproduce the algorithm based on our understanding, and it's just for the research purposes, and it's not for the commercial use.
Okay, I get it. Thank you.
Maybe on the left.
Hi, Shaurya Patel, UBC. So I had 2 questions, partly because I must have missed a part in the presentation. So why do you use swapping and recomputation? And my follow-up to that is, have you considered using lossless or even lossy compression, because that, and you still store all of your data on memory, just compress it, because that could have better performance than recomputation. Have you thought about that?
Okay, so yeah, I think the goal of VLM is to just serve the LLM as it is, like as if you just like running the LLM in general. So like lossy compression is basically change the accuracy, so it's like a more advanced technique that we haven't included in our current system. And regarding to why we need to do recomputation and do swapping, this is because so the output lengths of LLMs are completely, like, you cannot predict it. So there will be a case that you run out of all of the KV blocks, and then you have to do something, otherwise like the system just hangs over there. So you need to do like
Good, thanks.
Okay, let's go upstairs.
Okay, thank you for a nice talk. Wei Junyu from Tsinghua. So my question is about external fragmentation. You said that VLM has no external fragmentation because uniform allocation, right? So do you have any assumption of the current memory allocation of the deep learning training? Because as far as I know, the allocator in CUDA, they do not use like something like the buddy system or something like that, and you can allocate the memory at a random size. Even though you are not uniform, you will still have no fragmentation. So do you have any opinion about this? Thank you.
Okay, so the internal and external fragmentation we mentioned in the paper is happening on the application side. So it has nothing to do with CUDA. I mean, how CUDA actually manages the memory.
Yeah. I mean, you have said you compare with the buddy system in your paper, said the buddy system have some external fragmentation, and your work has no such fragmentation because you use a uniform allocation, right? So as far as I know, the CUDA allocator does not use a buddy system, and do you allocate it in the PyTorch level, not the CUDA level, right?
Yes. So we assume that the baseline system uses something like body allocation algorithm.
Okay, so you do this work in the PyTorch level, right? Not CUDA level.
Yeah, on the application level.
In the application level. Okay. Okay, thank you. Okay.
Go ahead.
This is Zhang from the University of Michigan. Thank you for the great talk. I believe the high throughput that VLM can provide is probably because of the high batch size that can be served at once. But I think if we set batch size too large, then it can rather decrease the throughput because of the many thrashing and too many recomputation. So my question is, I'm wondering how VLM chooses the best batch size for high throughput. Thank you.
So for most LLM serving use cases, as we demonstrated, like for example, in this result, you can see that the batch size is actually like surprisingly low. It's like from 7 to, like we improve it to 30. So it's like very, very low batch size compared to the existing deep learning workloads. Yeah. So in that case, we are like still very far from the other end of the trade-off that you have too big a batch size that you fully utilize the GPU compute and increase the latency, things like that. Yeah, we are still on the other end that the GPU compute is not fully utilized and we need to batch more.
Thank you.
And speaking of the thrashing thing, we actually have something like watermark algorithm, just like the operating system. So yeah, that also prevents the frequent swapping or frequent preemption.
Okay, one last question, I guess.
Petros Magnatis, Google. I was wondering, you mentioned in your examples how when you're doing beam search, a lot of the prefixes are shared, so it makes sense to cache them, you win from that. Have you thought about giving any external hints to the inference system? For example, a lot of prompts across examples have exactly the same prefix, so it would make sense to prioritize those blocks to stick around since you will always recompute them otherwise.
Yeah, actually, that's a great question. So we do have this in our paper, but we don't have time in our presentation. Yeah, you can, like for example, like share library in the operating system. You can cache a system prompt in our system and just like a shared prefix, and you can always just reuse the prefix instead of recomputing the prefix all the time. Yeah, that's in our paper.
Thank you. It wasn't planned. It was a random question.
Let's thank the speakers.